Plane mirror assignment, there's a few things we need to discuss as far as understandings go, so let's try to make sure those are all in place. So first of all, on the plane mirror diagram, we need to be able to recognize the parts. The first thing that we need to recognize on here is that this piece right here is called the normal. The second thing we need to recognize is the incident ray. The incident ray is any line that has an arrowhead that is heading toward a surface. That's what we call an incident ray. So that makes this the incident ray. Next thing we're asked to recognize is the reflected ray. The reflected ray is any solid line that has an arrowhead that is heading away from the surface. So that makes this here the reflected ray. Next, we need to find the incident angle. In order to find the incident angle, we have to go back to the definition of the incident angle. The definition of the incident angle is the angle between the incident ray and the normal. So we go to our diagram, we recognize that this is our normal. We recognize that this is the incident ray. And so that means the angle between the two is our angle of incidence. The last piece we have to define on here or mark on here is the reflected angle. The angle of reflection is the angle between the reflected ray and the normal. In this class, we're always going to be measuring angles to the normal. We're not going to be measuring to the surface. I want you to be aware that you will find evidence of that being given to you in textbooks or on the internet where they measure it to the surface. I say no to the surface, always to the normal, okay? Always to the normal. So there's the reflected ray, there's the normal. We mark the angle between. This is our angle R. And we're done question number 1. Question number 2 says, how many different rays can strike a mirror at the same point with the same angle of incidence? So how many, folks? One? Arfa, what did you say? Why 2? Well, I agree with 1. There's your angle of incidence. Once you've got that angle of incidence, you got that light ray going out that way. I agree with that. The second thing that we have to understand is, well, wait a second. Isn't this angle R have to be equal to angle I? So maybe that's what you're thinking about, Arfa, right? Is that, well, wait a second. If this was 30 degrees, well, then this has to be 30 degrees. So doesn't that mean I can go in at 30 degrees at this side and come out? So now that brings us up to 2. Here's the challenge. We aren't actually thinking about real three-dimensional space yet. Is it not actually possible for me to hit that spot at 30 degrees and rotate around at every possible 30 degree at that spot and get an infinite number of possibilities depending how small we actually increment that distance around that circle? So, 1, not the greatest answer. 2 at least is taking care of what we've been working with in the two-dimensional space, but the real answer would be unlimited because of the possibilities in three-dimensional space. Is that okay? Okay. So consider 3D. So 2, but you really should consider 3D. Next, for a given light ray incident on a mirror, how many possible reflected rays are there? How many? Why, Arfa? Okay, and all I'm asking you for is what physics are you using at this point to give us that answer. So remember there's 3 things we could have used for this lab or this assignment. We're using either rectilinear propagation, or we're using the law of reflection, or we're using DO is equal to DI. The perpendicular distance the object in front of the mirror is equal to the perpendicular distance the image is behind the mirror. So were you using any of those, Arfa, for your answer? Would anybody be willing to help? Logan. Landon, sorry. Law of reflection, absolutely. Law of reflection says the angle of incidence must be equal to angle of reflection. So in actuality, once you've chosen angle I, angle R has no choice. And so that means 1 is our answer there because angle I must equal angle R. We have no choice. It's locked in. So we go all the way from 2 to almost an unlimited number for 3D, but that's when you're choosing your angle I. The thing is once you've chosen your angle I, there is no choice in angle R. And that led us actually into that concept of light paths are reversible, right? Light paths reversible is directly due to the fact that light paths, once you've started on a direction, it's locked in because rectilinear propagation and law of reflection. Okay, if you see a person in a complicated series of mirrors, is it possible for them to see you? Yes. And we would say refer to what? Light paths are reversible? Yeah, and so using law of reflection, using rectilinear propagation, just like you did in the lab, that's really what I'm asking you to review there on that question. So that's just a review question. Fair enough? Okay. Next question, what's a virtual image? What's a virtual image? Edward.
The image in object forms in the actual mirror.
Yeah, and so and that's an okay definition. It allows us to kind of work with some mirrors, but I want us to change that definition. I think the different definition was, I gave a different definition on our lab that I gave you. Does anyone remember the definition I gave you on the lab? So a virtual image is where reflected or light rays only appear to cross or converge. Is that okay? So I'm taking away, all I'm taking from your definition, Edward, is I'm taking away the location piece that's referring to our optical device. Is that fair? Because in front and behind is going to become very, very skewed for us. It's going to be very, very unfamiliar when we hit lenses, because light can go through lenses. So there's an in front and a behind, but it's not quite as defined as it is in mirrors. Is that fair? Okay. Lateral inversion, we did that in class. We talked about this. Lateral inversion means left to right reversal. Yes? Question. Do plane mirrors have lateral inversion? I know. We went through this in class, remember? Does the mirror invert the image laterally? What inverts the image? We do. We do with our perspective change. We're facing in the opposite direction and that's what changes our perspective. The mirror gives us exactly back what we put into it. And so that's an important piece. Okay? All right. Now, a man stands 3 meters in front of a plane mirror. If he steps back 1 meter, what distance separates him from his image? Sorry, no, I read 2 questions there. How far is he from his virtual image? 6 meters. Yeah, he's 3 meters in front, so he must be 3 meters. The image must be 3 meters behind, which is a total of 6 meters between the two. If he steps back 1 meter, what distance separates him from his image now? 8 meters. Yep, because we added 1 meter in front. It also means we add a perceived 1 meter behind, so we have a total of 8 now. Last one. If he walks away from the mirror at 0.5 meters per second, what is his speed relative to his image? Exactly. It'll be 1.00 meters per second away from his image. Good stuff. Okay, now we're going to move into this question here, which is locate the images. The next section is just a group of diagrams to help us make sure we are applying the 3 laws. What were the 3 things, not laws, what are the 3 applications we're using on this question sheet? Rectilinear propagation, that's how light travels, straight lines. DOZ equal to DI, and just to make sure we're clear, it's the perpendicular distance the object is in front of the mirror is equal to the perpendicular distance the image is behind. That word perpendicular has to be a part of that. I know some of you, I was catching you the other day with some kind of funky angles, right? And what's the third one? Law of reflection, which is Angle I is equal to angle R. So these questions will use 1, 2, or 3 of these principles in their application. That's all we're trying to do is practice the application of those principles. So this question is asking us to locate the image. I'm not going to do all the questions, but we're just going to start off here, and I'm going to show you how I do this. I take my ruler, and I take number 15, for example, there. I get the ruler line, and I put it so that the line disappears on my mirror. Why do I do that? It's so that I have the edge of the ruler is going to be perpendicular to my mirror. This is a cheater method. If you're having troubles with accuracy with this, you get out your protractor and draw 90 degrees with your protractor. But for most incidences, if you're being very cautious with this, you can get pretty darn close to perpendicular and do a fairly good job. So I move my ruler up here until I take from over here, I get it lined up, and I slide along chugga chugga choo choo, chugga chugga choo choo, until I get to the object location and have the object on the edge of my mirror. Do you see how the dot's just on the edge of my line there? And I make sure I'm perpendicular, and I make sure I'm at the dot, and I just start doing this. I count. I do not use the numbers on my ruler. I count. Why do I count? Because math can make mistakes. We can make silly mistakes in math, but we aren't going to make mistakes in counting. We've got that one fairly well taken care of. So I count 1, 2, 3, 4, 5, 6, 7, and it's 7.5, 7.6, 7.7. Notice how I slowed it down there? I actually did that because I can't tell you the number of times I've seen students measure this one as a 7.2 or something else because they didn't slow it down. Slowing down and precision is what we're looking for here. We're not looking for speed and sloppiness. So I'm I'm going to count again because I lost count. 1, 2, 3, 4, 5, 6, 7.7. I'm now going to count 7.7 on the other side. 1, 2, 3, 4, 5, 6, 7 and 7 is right there. Too bad I got some other stuff in the way, but that's just the way it goes. And then what I'm going to do is I'm going to connect that with a dashed construction line. What are the purposes of this dashed construction line? Can you folks tell me what the purposes are? Yeah, our eyes can take this length and that length and look at it and say, does that look similar? My eyes aren't so great at that. But that's one thing that you can certainly do. You can clearly see a discrepancy there. And what's the second reason that our eyes can help us with? Our eyes can look at this and go, yeah, that looks perpendicular to me. We can see that. Okay, good. I'm going to do one more. I'm going to do this X one because it's off to the side of the mirror and it adds one more step. The Z one's the exact same process. To do the X one, we actually have to extend the mirror, so I put my ruler along the mirror. I actually always check, and this is, I think, drafting teaching I check to make sure my pen is actually on the line where I'm tracing this across. And I'm going to just dash over like so, and so continuing, we have the X, we've extended the mirror. The next thing we do is I take our ruler. I don't use the inch one, I use the metric one because the metric one has the millimeters measurements. I get my ruler so it's perpendicular by putting my mark line on the mirror, and my edge will be perpendicular. I chug it up, chugga chugga choo choo until I get to just at the edge of my dot. I check to make sure I'm perpendicular on my line, and then I count across 1.567. So then I count across the other way, 1.567. I make a dot. That dot is my image of X. I then connect the two with my construction line like so, and then this is my X image. We're now on side 2 with question number assigned. It says locate the image of the object, trace the light rays from the object to the eye, label the angle of incidence and reflection. So this is asking us to do just what we did before with some extensions. And that's really what you're going to see. I can tell you right here and right now, you can put a star beside this question. You're going to see this question on your hand-in assignment. You're going to see this question on your term exam for this section. And I'm pretty sure you're going to see a question like this on your final exam as well. So it's a very important question because it encompasses you being able to use all 3 principles that we want to apply here from mirrors. Is that fair? All right, so the first thing I want to do is I want to do my DODI thing. I put my ruler across so that I have room on both sides. I slide my ruler until I'm touching my object. I make sure my line is right on my mirror. I count across 1, 2, 3 point. It's actually between 1 and 2 as far as I can tell. So I'm going to go over here 1, 2, 3, and I'm actually going to try to make my dot between the two. I wouldn't be able to in science really tell that measurement other than I'd kind of have to choose 3.1 or 3.2. But when I'm doing these diagrams, I can do that estimation and put it about that same place to make it as accurate as possible. So this is my Z image right now. What I'm going to do next is I'm done step 1. Step 2. Notice I'm drawing these as construction lines with dotted lines. They're not solid. Step 2 says trace the light rays from the object to the eye. This is where we're actually using rectilinear propagation. We're tracing light rays. Light always travels in straight lines. So what we're going to do is we're going to say from the eye position, we're looking across, and we say, hey, look, from there to there, there's a straight line connecting those two. Light, it must be coming to our eye from that direction or we couldn't see it. What we need to do is recognize the light doesn't actually exist behind the mirror. So we draw this line, we draw it dashed behind like so, and then we're going to draw it solid in front, like so. I'm going to put an arrowhead on that light ray to go to the eye to recognize that this is not a normal, this is a light ray. The next piece that we have to recognize is that this is not where the light came from. Anytime you look along a light path, look back along a light path and see that it's got a dashed portion, that means it didn't really come from there. So we have to say to ourselves, where did it actually come from? Any ideas? It had to come from the object, from the place before. And how did it have to get there? Straight lines. Light has no choice. So then we can take our ruler, our light maker, if you will, because it's a straight line, it's a straight edge, and we're going to connect from that dot to that position. And we're going to do this like this, and we're going to go across, and we're going to put an arrowhead toward the mirror in this case, because that's the light that's heading toward the mirror. Any questions or concerns? We've now actually finished part 2. Yes? We're now going to go to part 3. Part 3 says label the angle of incidence and the angle of reflection. We want to remember, what is the definition of angle of incidence and angle of reflection? Any ideas? Angle of incidence is the angle between the incident ray and the normal. What's the angle of reflection? Angle between the reflected ray and the normal. So what do we need before we can do this? We need a normal. So we can do it 2 ways. We can grab our protractor, which I'm going to do just to be a little more accurate, or we could have used our ruler. But I'm going to put my protractor on here like so. Put my protractor so that my 0 line is exactly on the mirror, and I'm going to make a mark out here on the 90-degree point. I'm then going to use my ruler to connect from that point to that point right there, and that gives me my normal. Again, the normal is drawn as a solid line. Next thing I'm going to do is I'm going to put my ruler or my protractor back on here. I'm going to put my protractor on there, and I'm going to get it zeroed again, and I'm going to measure this angle right here. I notice that this angle is too short, and I notice this angle is also pretty darn close to short. So I'm going to extend those light rays just to make sure I can get them. So I'm just going to take this line and continue on a little bit further so it gets to the edge of the protractor. And this line here, I have to be careful with this line. This one is okay because light's heading that way. This one here, when I take it backwards, I can either use a pencil so that I can erase it when I'm done, or I could put it in as dashed lines so that everyone recognizes that's just part of my construction piece, one or the other. So I don't need to erase it because I just drew it in dashed lines. So I'm going to now go back to here to try to measure these two. And again, what do I do with my rulers and protractors? How do I measure on them? I count. Why do I count? Because you're going to make mistakes reading the numbers off. I guarantee you will. But you won't make mistakes counting. There's my 0 spot. I'm going to count over 10, 20, 30. I have 39 there. And I have 10, 20, 30. I have 37 there. So I have an angle I of 39 degrees. I have an angle R of 37 degrees. I'm a little disappointed in my values being off by 2 degrees. What would be my acceptable error? Well, my error should be within the error of measurement of my instrument. My instrument can measure down to 1 degree, so my error should be within 1 degree of each other. Now, that's not saying I want you to fudge your data. It means I want you to go back and make sure you're doing things accurately enough that they can be within 1 degree. Because I actually go at your assignments and your tests with a protractor to see with what you're saying to me is actually what you're measuring. Is that okay? So don't just fudge it. Go back and work on your process so that you can be accurate. Fair? Okay. Next one we're going to do is trace the light paths of these light as they hit the mirror. And it also says measure and label angle line, angle R. I'll tell you a little hint. Anytime you use angle line, angle R, anytime you use them, you actually have to measure them and you have to label the values. You can't just get away with doing whatever. Is that understood? Anytime you use them, you're using the law of reflection. Means you actually have to measure those values and write those values down that you used. Okay? So, here we go. Light ray strikes the mirror. What does the light ray do when it strikes the mirror? It reflects. How does it reflect? It reflects as a straight line, rectilinear propagation, and it must follow the law of reflection, which is angle I is equal to angle R. In order to do angle I is equal to angle R, what do I need? A normal. Are you getting this concept? We're going to need normals a lot. Okay, so here we go. We're going to put this on here. I put my protractor on there. There's my normal. And you know, I recognize right away that this line isn't long enough to measure, so I'm going to actually have to extend it. So I'm going to switch to my ruler. I'm going to extend this one back a little bit because I can't finish what I started until I actually have a better measurement for that. I have my marking for my normal, so I can actually put that in right now just to show what I'm talking about. There we go. Now I can go to my protractor, I go in here, and I recognize that we have a measurement of 10, 20, 30, 40, and it goes right between 2 and 3, so 40, 43 degrees is what I have. And what angle is this? This is angle I. This is angle I. Now I know I need a 43 degree angle on the other side. So I can do this. I can go back on here and make sure I'm exactly in position, and I count, right? I don't measure. 10, 20, 30, 40, and it's 3 degrees, so I make a dot right there, and that's my value I'm going to connect to. And I need to show that this is a light ray by putting an arrowhead on it. They aren't light rays unless there's an arrowhead on it. And what angle is this? Angle of reflection. And I've traced that light ray. Fair enough? Next light ray. This one kind of looks like, oh, what the heck? There's no point in doing this until you put the protractor on there. And you put your protractor on there and go, oh my goodness, you tricky devil, Mr. Wright. There's a couple degrees off there. Yes? So we're going to have to work through this. But again, it's too short for my protractor, so I'm going to go and I'm going to extend this light ray back a little ways. Again, I take my pencil to make sure I'm actually on the line before I start drawing behind the line. That's one of the mistakes people make, is they just automatically kind of set it up, but they don't check that their pencil's marking on the line. So you just check. See, when I do that, you don't see that I've drawn anywhere other than on top of the line. So you know that we're on the right spot. I'm going to take my protractor back, put it in spot right here. And I look back along my protractor, and I see that this is coming out 2 degrees on the right hand side of 90 degrees. So this here, right in here, is 2 degrees. What angle would that be? That'd be angle I. But in order for it to be angle I, what do I need? I'm going to need a normal. And so this is what I'm going to do. I'm going to put this back on there, measure up my 2 degrees. I'm going to make a mark right here so I can put in my normal. And while I'm here, I'm going to count 1, 2 degrees on the other side and make another mark. And so now I can draw in my normal. At that point, it's going to get little bit tight and close there. And I'm going to mark in my reflected ray. It's going to come in. It's going to look also very tight. And I'm going to put an arrowhead on that, showing that that's the light ray that's leaving. And I've drawn in that. What's the piece I haven't done yet? I haven't labeled it, so right in here, this is going to be angle R, and it is 2 degrees. Are we good?
It's a little bit dirty to make such a small angle.
Yes, it is. Sharp pencils, those mechanical pencils, beautiful pieces of equipment for working on this stuff. Okay, you can erase them. They're nice and sharp, fine points, good stuff. All right, so now we're on to question number 11. Question number 11 is the question that asks us to look at these two light rays and find the source. So this is a question that says find the source. It's not like this question that says tell me where they go. This says find the source. Whenever you're asked to find the source, and we did this before where we said find the point source, and we had diverging rays and we had parallel rays, remember those? Find the source. You have to trace them backwards. It's kind of like a form of triangulation. So what we need to do with this is we need to trace these lights backwards. So we take this light ray and we put our ruler on it and we go backwards. We're using a ruler because we're following rectilinear propagation. So that light ray comes from somewhere back there. We remember from our previous lab that triangulation is using two lines of sight. If you trace them backwards, you can find out where they came from. So this other light ray should let me do that. So I take this light ray and I go backwards and I go, oh my goodness, it's not going anywhere near this one and it hits a mirror. So what do I do now? Why am I going to get a normal?
So that you can draw the incident.
Oh, very good. This is my reflected ray is really what this is, so I need to find my incident ray. And if I think about it, that's what I need to do. Before I go any further though, I'm going to need to extend this light ray because this light ray isn't long enough for me to measure with my protractor. It's just one of those things you get used to after a while, that you're going to need to raise certain length in order to work with your protractor. I'm going to put my protractor on here, put it on like so, and I'm going to do this, make a mark so I can do my normal. And while I'm here, I'm also going to measure the angle, and I count 10, 20, 30, 40, 50, 52 degrees. This is my angle R, and it is equal to 52 degrees. What was my rule about angle I and angle R? Anytime you use them, you have to draw a normal, very good, and you have to label them every time. If you use them, you have to label them with the value you used. Now I'm going to go and do what Edward said. I'm going to go find my angle I, my angle of incidence, because this is my reflected angle. I'm going to go make sure my protractor is on the spot and it's set up. And I'm going to count on the other side. 10, 20, 30, 40, 50, and I'll make a mark at 2 degrees. Get my ruler, and I can trace this light ray back to this direction, like so. And I put an arrowhead on it. I'm going to mark my angle I is equal to 52 degrees. I'm taking care of all my business before I get carried away, showing my work, showing exactly how I got there. And then look at that right there. This is the source. Right there, where those two cross. So it isn't good enough just to have those light rays cross. You actually have to say, I recognize that right here where those two cross, that's my source. Good? Here we go, question 12. Okay, question 12 is, as accurately as possible, draw the image of the 7 in the mirror. And you notice we have this image of a 7. We want to draw it in the mirror. What are we going to use? What principle allows us to locate an image in a mirror? Is it law of reflection? Is it rectilinear propagation? Or is it DODI? It's DODI. This question is all about DODI. So I'm going to need to do DODI. What we want to do, though, is we have to recognize that I don't want to do DODI for every single part in here. That would take me forever. So I need to find some key points. Just like when we did our shadow diagrams, there was key spots and everything in between is just everything in between. So I recognize that my endpoints, that endpoint, that endpoint, and that endpoint must be key spots. I also recognize that between this endpoint and that endpoint, it is a straight line. So that would mean if I get these two endpoints as their images, there should be a straight line connecting those two. So that's not an issue. In between here, this is not a straight line. So we're going to need to take extra measurements between there and there because the question said as accurately as possible to draw in this image. Not kind of, sort of, not kind of guessing, but as accurately as possible. So the first thing we're going to do is we're going to set up our ruler perpendicular like so. We're going to come onto here, and I'm going to measure this point. And it's 1, 2, 3.5, 6, 7, 8. So I'm going to count 1, 2, 3.5, 6, 7, 8, make a dot, and I'm going to connect those two with my construction line so I can keep honest about my measurements and everything else. I'm going to do the same location. I'm going to measure the other end of that piece, keeping on the same line. I'm going to count 1, 2, 3, 4, 5, and it's 5.5. I'm going to count on this side 1, 2, 3, 4, 5.5 and make a dot. I recognize that this should be a solid line between those two because that's the top of our 7. Fair enough? Now, what I'm going to do is I'm also going to do the bottom part of our 7. And I'm going to measure 1, 2, 3, 4, 5.1, 2, 3, 4. So 5.4, 1, 2, 3, 4, 5, 5.4, make a dot, and connect the two with a dashed line so I can recognize what I'm dealing with. And that's my dot. It'd be nice to connect dot to dot right now, but that's not what we want to do. Okay? What we need to do is we need to work in this area. We need to work in this area and make it as accurate as possible. Okay? So we're just going to continue working with this, moving down a little bit at each time. And again, making sure we're perpendicular. Measure over 1, 2, 3, 4. And this is 4.5, 4.6, 4.7 over here. 1, 2, 3, 4, 4.6, 4.7. Make a dot. And then we're going to connect those two with the dashed line so it shows our work and it shows us that we're doing perpendicular measurements. Moving down again a reasonable distance to be as accurate as possible. We could do 1,000 lines in here, but that's just not something we're going to accomplish. So 1, 2, 3, 4, 5, 5.1. 1, 2, 3, 4, 5, 5.1. Make a dot. Connect those two with a dashed line. Moving down a reasonable distance. And we're going to measure 1, 2, 3, 4, 5. This one is 5.1, 2, 3. And we're going to do 1, 2, 3, 4, 5, 5.3, make a dot. And connect those two with a dashed line. And I'm probably one more, and I should be pretty good. So this is 1, 2, 3, 4, 5, 5.4. 1, 2, 3, 4, 5, 5.4, make a dot, and connect those two with a dashed line. And so this is giving me, now you can see I've got this pattern. And guess what we get to do now? Something you haven't done since kindergarten. You get to connect the dots. Isn't that awesome? We're in physics class connecting dots. What a crazy thing to do. So you connect the dots, and you can, with fairly, accurate feelings, that you've done a reasonable job of duplicating that. And you get this perception of what we look at in mirrors, right? Mirrors give us exactly what's in front. If something is further away, it's further in. If something is closer, it's closer. Yes, and that's what we're getting. Here we're going to do number 13. As you can see, we've just been scaffolding question on top of question, just adding a minor change every time so that when we get to questions like this, you can manage how to do it. This question says, as accurately as possible, so we understand that piece, draw the image of the object in the mirror, so we want the image, and then trace the light rays from the vertices 1, 2, and 3 to our eye. So, much simpler diagram because we have a triangle now. The only things we're going to have to worry about are the vertices, the corners, right? So what we need to do is find the image of this triangle by finding the corners, and everything else in between will be a straight line. Fair? Okay, how am I going to find the image? What is it, the principle that I'm using? We're using DO is equal to DI. So we're going to put our ruler on here. We're going to get it perpendicular to the mirror. We're going to slide it up to our vertice number 1. And I'm going to count 1, 2, 2.5. I'm going to count on this side 1, 2.5. 1, 2.5, make a dot. And I'm going to connect the two with a dashed line just to show that I'm doing things right. And that's my number 1. I'm going to do the same thing down here with my number 2. I'm going to get it on the ruler. Actually, this is number 3. I'm going to do 1, 2, 3, 4.3. And I'm going to do 1, 2, 3, 4.3, make a dot, and connect those two with a dashed line. My last one is the number 2 here in the middle. I'm going to measure over once I'm on the ruler. There we go. 1, 2, 3, 4, 5, 6.2. Measure over 1, 2, 3, 4, 5, 6.2. Make a dot, and we're going to connect that with a dashed line. I'm now going to actually connect these because I just love connecting the dots. I miss kindergarten as much or more than you folks do. Connect that one right there. I'm going to connect this one right here. And I'm going to connect this one right here. And voila, we have the image of this object in that mirror. The next question is, okay, now show me how the light rays get to the eye from each of those vertices. Okay? So we're going to start with vertice number 1. In order to trace light rays, we've done this already before. We don't actually care about the object, we care about the image. So we're going to talk about this is number 1, this is number 2, and this is number 3. Those are the images of 1, 2, and 3. I'm going to say light travels to my eye from 1. What kind of path must light follow? Must follow rectilinear propagation, must be a straight line. So what I'm going to do is put my ruler on there and go from that vertice to my eye. I'm going to draw a line that's dashed in on the back side of the mirror. Why is it dashed behind the mirror? Because it's not actually there. And then I'm going to draw it solid in front like so. And I'm going to put an arrowhead heading towards the eye. Always do that as you do it. I've had many students over the years that, oh, I'll put my arrowheads on later or whatever. Well, they hand in assignments to me without arrowheads on them. They do tests for me without the arrowheads on them. Make it a part of your procedure, then it'll always be there. The next thing is, well, where did that light ray come from? Well, this is the image of number 1. Shouldn't the light ray have come from number 1? So what I'm going to do is I'm going to do this. I'm going to draw a line from where vertice number 1 is to where the light ray last was known. I'm going to put an arrowhead heading towards the mirror because light is leaving the object and heading to there. Do I need angle I and angle R to do this? No. So do I need to label angle I and angle R here? No. What was my rule? If you use angle I and angle R, you need to measure them and you need to label them. In this case, I used 2 principles. What are the 2 principles I used? Rectilinear propagation and DO is equal to DI. Thanks, Unisa. All right, so now I'm going to do number 2. Here we go. Here's number 2. I'm going to draw a line from number 2 vertice image to the eye right there. I'm going to draw it dashed behind because it's not actually there. I'm going to draw it solid in front. And there we go. We're up to the eye. Then I put an arrowhead on it going towards the eye. Now I say to myself, is that really the whole path of that light ray? No, it isn't. Where did it come from? The original object. So now we're going to say, well, light, we know is there somehow. Where did it come from? It had to come from here. So we connect those 2 with a straight line because light always travels in straight lines. Thank you very much, light. I can't tell you how much I appreciate this because I would sure hate to work with squiggly wiggly lines all the time because it'd just be so darn random. So here we go. Straight line up to there like so. And I put an arrowhead on it heading towards that. And when I first looked at this, I was starting to think, oh, well, it's not actually going to be possible for them to see vertice number 2 because the triangle would be in the way. Is that true? The triangle isn't in the way, is it? The light doesn't travel from here to the mirror. It travels from the vertice to the mirror there and gets to our eye. Kind of neat, huh? I think so. But I'm a physicist, so I'm kind of a geeky that way. All right, we're going to do the last one, and that is we're going to look at number 3. So again, you take from your eye position, you're looking at number 3. You draw a light ray from the eye to number 3, recognizing it's solid in front and dashed behind because it's not actually there, but it's sure nice to use as a reference point. We put an arrowhead on it heading towards the eye because this light is hitting the eye. That's how we see things when light actually hits the eye. And then the last thing we say is that the actual whole light ray? Is that where it all came from? No, anytime you see a light ray with a dashed portion, it means you haven't traced the full light path. So we're going to say, hey, it came from actually number 3. And again, I was worried about maybe some obstruction here. But look, lo and behold, when we draw a line between the object number 3 vertice and the location where the light ray was, there is absolutely no problem whatsoever. And we're done that question. Folks, all right, here we go to number 14. It says images of all 3 objects in a plane mirror. If the woman can see the image, oh, that's this question down at the bottom. So we actually need to move things so you can see the question we're talking about. So there's the question we're really talking about. I don't care about these questions. These questions don't matter to me right now because I can't answer any of these questions until I've done what? I need to finish my diagram. My diagram is the answer. So what we need to do is we need to finish the diagram. What we need to do without us being told it is we need to find the image of each of these people and dog in the mirror, and then from there we can try to answer the question. So what I need to do is find the images. So here we go. This is we've done many times already today. We measure in front 1.8. We measure behind 1.8. Make a dot. We connect the two with a dashed line. That is M image. I want to do dog and I want to do woman, but I can't do it until I extended the mirror because you need the mirror to be able to measure DODIs. So here we go. Da 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 da. And da 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 da. I'm now going to measure the woman. I get my ruler on here, perpendicular, and I'm counting 1.9. So I got to go back 1.9, make a dot, connect the two with the dashed line. I need to do the dog. I go over here, set my ruler on perpendicular, and I measure this. This one I get 1 point a little bit. So 1 point, I'm just past 1 on that, and I make a dot. So this is my dog's image, and this is the woman's image. Now I can start to answer these questions about do you see this or don't you see this? But we have to recognize, how do we know if we see something? This we did the other day. How can someone see something? What's the key? Yes, sir.
Light and eyes.
Light and eyes. Yeah. Light has to be able to come to the eye, but in order for it to create an image, that light has to come from where? It actually has to come from the mirror, right? So there has to be a path between the eye and the image that crosses the mirror. So it says, can the image of all three objects in the plane mirror, actually we've done that now, if the woman can see the image of the man in the mirror, why or why not? So here we go. I'm just going to do this. I'm going to put a line there and a line there, and I look at this line, and I see that lo and behold, this line does not actually cross the mirror. And because it does not actually cross the mirror, that means reflected light cannot strike the woman's eye, which means she cannot see the image. And so that's my answer for B. Answer for B is no, and I can certainly draw this image in here, but I'm going to do this. I'm going to draw it all dashed. Now, I see some interesting looks in there, but I'm seeing a clear miss of my mirror here. Now, if yours is done and done correctly, which I would check if you handed it in to me, I would see if your DOs and DIs are measured accurately, and you happen to get it because it's darn close for me, but I have evidence that says no. And my evidence is what I'm using to make my conclusion on. Is that fair? Okay. Now, if you did a poor diagram, but at least you have the right answer, at least I can find some part marks on an assignment like this, right? Because then at least you understand the physics, you just had a little bit of a messy diagram. Okay, so the woman can't see the man. Can the woman see the image of the dog? So for that one, the same check is true. I connect the woman's location where her eye is with the dog, and look at what I get to do. I put a dash line behind, but oh, lo and behold, it actually comes, and I say yes. Yes, she can. I can certainly trace that light ray back to the dog, but it's not essential. I'm just checking to see if it worked or not. Next question. The woman can see the image of herself. Can the woman see herself? No, she cannot, because the light ray does not strike the mirror surface. Next question. Can the man see the image of the dog? Again, we have to go from the man's location because it's the man trying to see the dog. We do dash line behind, and oh my goodness, look at that. I cross the surface of the mirror, which means the man can see the dog. Can the man see the image of himself? Can he? Sure can. If you connect the man with his image, you see that there is a straight line path there, and that means light rays will go to his eye from that location. So that is also a yes. Can the dog see the image of the man? Well, you can do this from the dog and say, does the dog see the man? There's his location. And you can go, look at this, dash behind, and you can go solid in front. But you can also recognize this. Notice where the two lines cross. This is the man seeing the dog, and this is the dog seeing the man. This is the old question that I just finished dealing with you that says light paths are reversible. Correct? If the man can see the dog has to be able to see the man. Okay, number 15 says, in the following diagram, which eyes can see the image of the object in the mirror? Explain why or why not. This here is the object. I had a person clarify that the other day. Not this. This here is simply a barrier. So we have to be aware that the barrier is an opaque barrier. What does opaque mean? Light cannot pass through it. So we have to be aware that that's an opaque barrier. All right, so how do I answer this question? The way to answer this question, first of all, is what do you have to do? You've got to find the images. That's always our first step in this, folks. Have you noticed there's a pattern here? Locating the images is the key. So to locate the images, I'm going to find this object's image in the mirror. So here we go. I'm going to put my ruler on perpendicular, get it up to the edge of the object. I'm going to count up to it and say, oh, 1, 2.4. So I go down 1, 2.4, make a dot like that, and I'm going to connect those two with a line. Now all I have to do is say, from eye position number 1, there's my eyeball, there's the image. If I connect those two, does that path cross the mirror surface? Does it? I1. No. And the reason for that is the line of sight does not cross the mirror from where the image location is, so light cannot come from the object, strike the mirror, and hit the eye. And the reason for that is angle I must equal angle R, right? If this light travels from here towards there, it cannot reflect at an angle that reaches the eye. It's forced to go at an angle that's above it. If this person moved up, they'd be able to see it, but they can't. Now we're going to do eye position number 2. Again, we're going to take from the eye position, we're going to go down here, and we go, oh, look at that. I can connect from the image to the object, and looky, woohoo, I have light paths hitting the eye. So can he see it? Well, we actually aren't sure yet.
The following...
Is it recording this?
Here we go. We actually, on the previous question, we didn't care about the incident ray. We only cared about the reflected ray. But on this question, there's an opaque barrier that we have to be aware of. And so what we need to do is connect from that location to the object. And this one here, when you do this, you should run into some issues. You should see that the light ray actually cannot get there because the opaque object is in the way. And so this makes this one a no. Oh my goodness, we're 0 for 2 on this question.
Do we need to figure out like the incident angle to do that one?
No, we don't, because we've used the object location, we've used DODI, and we've used rectilinear propagation. If you use DODI and rectilinear propagation, angle and angle R follow along.
That's right.
Or if you use angle I and angle R and rectilinear propagation, DO and DI follow along. So, but the only thing is I find it much easier to work with DODI and rectilinear propagation than I do to work with angle I and angle R.
Okay.
So that one's no good. So we got to try this last one. Here's the last one. From the eye, we're going to draw a line, dash behind, and it crosses the mirror. So I get to draw that solid in front. I'm going to draw that light ray to the eye and go, ooh, I'm getting excited. Maybe this eye can see it. And I go from there to there, and I draw those two together, and voila, I have a full light path. So yay, number 3 can see it. Now you have to write that out because it does say, please notice it says explain. It's not just a no, yes type answer. You have to explain it. And thank you very much. So we're moving to question number 16 here now. We finished the question 15. This lesson is asking us to, as accurately as possible, determine the location of this image for the given object, then determine the location where the person can stand to see the whole image, show all your work. So this is a wonderful combination question again. The first step of it is to find all of the image locations. Okay, so to find all the locations of the image, we must recognize that this object is actually beyond the edge of the mirror. So our first step is going to be to extend the mirror. We put our ruler right on there. Again, the technique is to run your pen along there to know if you're along it. If you're not on the mirror exactly, when you run your pen along, you'll see a pen mark beside. You go, oops, that's not what I need. So running your pen along there gives you that technique that allows you to know that when you go beyond, you're actually going to be on the place. Oops, I should have drawn that as dashed, but that's my bad. So next thing we're going to do is we're going to do DODI. That's the principle we're going to apply here. We're going to put our ruler on so it's perpendicular to our line like so. We're then going to measure our DOs and DIs from that position. So I count over 1, 2, 2.2 centimeters. So I count this way, 1, 2.2 centimeters, put a dot, and connect the two with a dotted line. That's the front of my triangle. I'm then going to count back 1, 2, 3.9, count back 1, 2, 3.9, put a dot, and that's the end of my triangle. I can connect those two dots. That is my image base of the triangle. Next thing I need to do is I need to go up here to the mirror and find the tip vertex of this triangle. So I'm going to make sure I'm on the mirror, perpendicular, 1, 2, 3.9. Oh, that should be 3.9 because the other one was 3.9. 1, 2, 3.9, make a dot, and connect that with a dashed line. We use those dashed lines to give us the perception of perpendicularity and whether the DOs and DIs are actually truly proportional. I can then connect this vertex to this point right here, and I connect this vertex to this point right here, and I have drawn in the image of the object. Notice it gives us the appearance that it is actually flipped or something, but in reality all it is doing DO is equal to DI every single time. Now we want to know where this person must stand in order to see the image of the object. If the person stands down here, will they see the image of the object? If I draw anywhere down here, we know that the person can't stand behind the object because the object blocks their vision. So if I go down below, I can connect from that point of the object to there. Is that visible? That's not visible. Anyone tell me why this is not a position of visibility?
The light source can't reach.
Because this line of sight does not cross the mirror. If you're not crossing the mirror, that line of sight, that means no reflected rays can come to you. You need to have the mirror between you. So that means the only place we can stand to see this is where? Well, it's not down below. We must try up high. Right? The question is, where do we put that? The way to do it is we need to connect the extremes. We need to connect the extreme of the mirror with the extreme of our image. So I'm going to make a line connecting this bottom tip of the mirror with the bottom tip of our image. I'm going to connect that line dashed behind the mirror, and I'm going to make it solid in front of the mirror. At that point, I know that light ray strikes the mirror and is going to be able to come from this object up to the mirror and reflect. Angle I is equal to angle R, and it will get to the eye of the person. Now, I need to also check to make sure that that location will allow me to see everything else. So I'm just going to do this. I'm going to go from that position and go, okay, every time I move my ruler, that ruler will cross the mirror every time after that location, will it not? So I'm going to do the other extreme then, from that position to the top extreme of the image, dashed behind, solid in front, and that tells me this light ray can strike the eye from this piece of the mirror. So this tells me anywhere up there is visible. Any questions? What two principles was I using for that diagram?
Light travel on straight lines.
Absolutely. I was using light travels in straight lines, rectilinear propagation, and Edward? We were using DOs must equal to DI. Okay, so now we're going to work with this last question, number 17. And number 17 is an interesting beast because what I'm trying to do is introduce the possibility that the reflective surface does not always have to be a plane. And so I'm introducing a spherical shape as a reflective surface. So we can imagine that the inside of this is reflective and the backside of this is the backside of a mirror. So this is a curved mirror or a spherical mirror. What we want to do is just trace the path of the light rays. To trace the path of the light rays means we take them forward and see where they go. So what I'm going to do here is I'm going to take this light ray here, and I'm just going to make sure my ruler, do that to make sure I'm on the line, and then I continue that line until I strike the mirror and I stop. And so when I stop the mirror, I have to remember that we have this rule that says if light strikes a reflective surface, it must follow a law. What is that law? Law of reflection. And what does it tell us? It says angle I must equal angle R. So what I need to realize is I should be able to reflect this light ray off this curved surface. And it has to follow the law of reflection, angle I is equal to angle R. In order for that to happen, what do I need? We need a normal. And so one of the things I taught you the other day was a normal to any curved surface is a line between the center and the curved surface. Why? Because that line between the center and the curved surface is perpendicular to that point of the surface where the center connects to the surface. So we can actually draw in a normal here because you have the center value given to you. You're all wondering what it was there for. It is just there for this purpose and this purpose alone, and that is to draw in a normal right there to where those two strike. Now what I'm going to do is I need to follow the law of reflection, so I'm going to put my protractor at the point where those two meet up. So here we go. I put my protractor on that point where it strikes the mirror, and I recognize that I'm measuring from there to there, so that's 10, 20, 30, I have 32 degrees. So I have 32 degrees here, and that is my angle of incidence, and it's 32 degrees. What do I have to do now? I have to reflect this light ray. It has to reflect off of the mirror, and it has to cross the normal. This was brought up last time we were working on questions, that whenever you dealing with the normals, one value is measured on one side of the normal, the other value is measured on the opposite side of the normal. So we need 32 degrees on the opposite side of the normal. So to get 32 degrees on the opposite side of the normal, again from that point, I'm going to count over 10, 20, 30, 2 degrees. I make a mark, and then I'm going to connect from there to there with a straight line. And that's my light ray leaving. And this is my angle R is equal to 32 degrees. So we've done one light ray at this point. We want to do a second light ray. And you take this light ray in, parallel to the light ray we had to begin with, just following that same path, hit the mirror. Once it hits the mirror, what do we use? We use the normal from the center, so we're going to take the normal from that point to there, connecting those two pieces right there. That's my normal, and now I can measure my angle I. So I put my protractor on here, and I measure my angle I, and I get 10, 18 degrees. So I have an angle I equal to 18 degrees. What would my angle R be? It's 18 degrees. And where would it be? On the opposite side of the normal. So we're down below the normal here. We have to go above the normal next. So we have to do 18 degrees on the opposite side of the normal. So we'll put my protractor on here so that I'm opposite the normal like so. And I count up 10, 18 degrees, make a mark. I'm then going to connect from that point to that point like so. And I get angle R equal to 18 degrees. Now I'm going to do my last one. Are you folks okay? Is this, yes? Any questions? I'm going to do my last one. I'm going to take my last one in. Like so. I then am going to draw in my normal, just like I've been doing for all of these. Normal always is going to come from the center to that point. I'm going to measure my angle of incidence, put my protractor on. Measure my angle of incidence, and this time it's quite the angle. It's 10, 20, 30, 40, 50, 55 degrees. So I have an angle I equal to 55 degrees. I need to mark an angle R. Angle R has to be on the other side of the normal. So we're down below to begin with, so we now have to go up above. So 10, 20, 30, 40, 55 degrees. Make a mark. How you folks doing on that whole counting concept? Are you feeling all right about it? Counting working for you? How many of you are still holding out trying to actually measure with the numbers? How many? Landon, you are? Of course you are. You're just that kind of guy. All right, there we go. So this is my angle R is equal to 55 degrees. What I'd like you to notice about this diagram is that the light rays actually all head toward the middle. Can everyone see that? When the light rays reflect, whether we come in above the top half of the reflective surface or the bottom half of the reflective surface, light ray comes in and goes toward the middle. Light ray comes in and goes toward the middle. Light ray comes in and goes toward the middle. Yes?
Can you explain why the normal, that point C that you have again?
Well, it's just a math relationship that says any line you draw, line segment you draw from the center to the outside point of a circle or spherical object will be perpendicular to that point of the object. So that's a definition of that piece of math. So for us, when we want a normal that is perpendicular to the surface. So if we've got a light ray that strikes the surface at this certain point, we need a normal to measure angle I and angle R. The fastest way to get a normal is to draw a line from the center.
So like the radius of the circle?
Yeah.
Okay, I
Yeah.
got it.
Okay. So this is the beginnings of where we want to go next in class. This is the beginning of spherical and curved reflectors. Is that okay? The first thing I'd like you to notice is that there's actually a really neat relationship here where you see two of these reflectors right here that actually cross at very nearly the same point. Did that happen for you folks? Did you have these two crossing very nearly the same point on this line that heads out from here? Yes? And then the last thing you notice is the one that comes right near the edge, the furthest out one, doesn't even come close. Yes? And so those are some principles and things we have to learn about light rays and how they work with curved mirrors. And we're going to start with our curved mirror reflecting PowerPoint that I have ready for you folks. So that's what we're doing next. Okay? Thank you.